Hey everybody, Dave Lindbergh in Hong Kong with another episode of the THD Podcast. Today we have another company coming out of Montreal. Seems to be something in the water there. A company called Echosonic, and they're doing physical reservoir computing. So it seems to me, and I like to kind of paraphrase before we get into it. We'll find out if I'm right, but it's an edge computing technique to kind of process signals on the edge rather than taking from the microphone signal up to a cloud and back. So it's creating efficiencies there. So we're going to find out about that. Without delay, let's give a thanks to the ALTI Association, our sponsors. So we encourage everybody to check out their website and get involved with some of the events that ALTI is putting together. So without delay, let's say hello. Good morning, Simon in Japan. How are you?
Morning all.
Okay, and Marie-Eve Desrochers in Montreal. Thanks for joining us today. How are you?
Good, thank you.
Good. Yeah. So we heard about Echosonic, and it's just so everybody knows, it's an early stage technology. It's in the development phase. So that's kind of the position right now. It's you can't buy it just yet, but we're working on they're working on developing it and getting it ready for the market, and we're going to find out what's it's all about. So I guess take it away and tell us about Echosonic.
Yeah, absolutely. Thank you, David. So can you see my screen at the moment?
Not yet.
Okay. Yeah, thank you, David. So as you see here, we are an edge computing company, and we try to bring sound recognition processing directly on the microphone sensor without adding any other components to the system to make it more efficient and power efficient and cost efficient.
Mm-hmm.
So actually, we know that sound recognition is everywhere. And usually we would like to do it on a one single chip to do sound processing as a DSP. But unfortunately, there's no affordable chip that can handle large AI model with high accuracy directly on the edge. So what people are doing usually, they will rely on the cloud platform to do the processing of their sound and to do the recognition of their sound. And when I'm saying sound, it's not just like a voice and speech. It's also all kind of sound. As you want to recognize a specific failure in a machine, an engine, you want to detect that there's abnormal sound. So you can rely on a platform, AI platform, to detect that this is not the correct sound. So here, what is the problem with cloud platform? First of all, it's super expensive at scale. So if you have to upload and download each time data and processing on the cloud, this is very expensive at scale. There's latency problem with that also, which is not acceptable for some critical application. There's privacy concern as well, because your data are going directly to outside your environment. And you need also a constant internet connectivity and a stable one. So actually what we propose at Echosonic is to bring everything directly in the sensor. So that's super easy, that's super simple idea, but there's some challenges. As I mentioned before, current chip cannot do everything at once. So what we are proposing, it's something based on physical reservoir computing technology. And of course, just stop me if you have any question. This is super technical.
Okay.
Actually, what we try to reproduce inside the physical device. So inside the microphone itself, we try to reproduce what a recurrent neural network is doing. A recurrent neural network, it's actually a paradigm in machine learning to actually connect different nodes together that will create a process that can process data and extract feature in order that at the end you can do a classification just by combining with weights some of the feature together, and it gives you a class at the end. So here we use the microphone dynamic to create this kind of a mixing of the audio and extract the feature that can then be combined to do the classification. And we want to integrate that into a MEMS microphone for efficiency. A MEMS microphone is already super efficient in terms of power consumption and also in cost. So we can use actually the dynamic in the microphone to create what we call a nonlinear oscillator. Because a physical reservoir computing, actually, it's based on this principle of having a nonlinear oscillator that will be able to transform your sound in a more complex dimension. So your sound is characterized by two things. You have your amplitude, you have your duration. This is a time series signal, essentially. When you want to do classification or feature extraction of the sound, usually you will transfer it into its frequency domain by applying a digital signal processing on the digital format of your audio. So you transform it into what we call a spectrogram. So frequency versus time, frequency, amplitude, time, whatever, this kind of space. And then you can start seeing some features that are associated with classes. So you can, for example, in here, it's a really silly example, but you have class 1, which is a bird, you have class 2, which is frog, and in frequency domain, there's some difference between those two kind of classes. So usually you will take this spectrogram that has been processed using a DSP or using the cloud platform to inject into a classifier, essentially a convolutional neural network most of the time. And
go. Paraphrase, so like the MEMS is going to be using the processing on the edge to kind of detect the impulse that's coming in and then almost instantly classifying them into, is that the wind noise, or is that the person speaking, and these kind of classifications based on this?
You mean the regular way to do classification?
No, like this way. So it's actually happening right on the edge, that the microphone, it's nonlinear. It's actually separating these noises into different classifiers right then and there.
Yeah, that's exactly what we're doing. And it's what I will explain just here.
Okay.
So if you see, you're too fast for me, actually. So if you can see here, the last, I will say the last plot I done here, it's how the physical reservoir is working. So instead of having a certain, let's say, feature in your sound, so you have your amplitude, your duration, you digital the sound, and then you apply the processing, the physical reservoir computer will extract some new feature of the sound directly when it's entered into the sensor itself. So the dynamic, the microphone itself will amplify some of the feature, will combine some of the feature in time, in amplitude, and in frequency to create new kind of features. So at the end, my output signal contain more.
Are you talking about the physical characteristic of the microphone? I mean, it's acoustic behavior, not in a digital domain.
Exactly. So at that moment, we are still in the analog domain. So before, when we were doing some sound analysis to extract feature, it was in the digital domain all the time. And with the physical reservoir, you can do some sound processing directly at the sensor level from the moment the sound pressure enter your microphone, enter your system. And the output of your system will already be sound that has been processed by the physical system. So here, what the physical reservoir is doing, it will extract what I call here virtual dimension. So you have it's not necessarily frequency, amplitude, time. It's kind of a combination of all of that. And I will show you here what actually it's doing inside the reservoir itself. So you have your input signal that coming into a system. The system here is a microphone. The microphone has been bring into its nonlinear regime. So you are in a regime where I would say, when you have an input and an output, and you just change the amplitude, it's not linear necessarily. It will have some modification of the signal at this moment. And you vary in time the behavior of the microphone in its nonlinear regime. So you will just change a little bit the response of the microphone in time. So at the end, you will have different outputs for the same device, as if you had multiple devices at the same time. So you have a superposition of states of your input signal at this moment.
I'm just thinking like trying to I always try to dumb things down because I'm a marketing side, but is this almost like a multi-touch capacitive in the sense you're using the MEMS membrane as like almost like a multi-touch? So there's multiple signals hitting it and you're separating them for different and then categorizing them post-process. So you're basically pre-screening the inputs?
That's a good intention, but it's not exactly that. Okay. It's more that we modify the behavior of the microphone. So your device is still the same, but you have a different response of your device in time. So when your signal coming in at a certain time 0, you have a certain response of your microphone. At a time 1, you have a new response of your microphone. So you can have, for example, if you have a constant signal, at the end, you will have superposition of different outputs. Even if it was the same input at the beginning, you will have different outputs at the end that are all combined together. And what we can do with that, now I passed to the classification part. So here we were in the reservoir, how we can extract the feature, and now how we can do the classification using those information. So here, those little ellipses represent my different states, the different, I would say, response of my microphone in time. And I had actually trained a model, a very simple model. It's really simple. It's more simple than a CNN, for example. So it requires less training. There's less comparator in it. It takes less space as well. This is the main value here. And we can actually just extract all of those response of my microphone, and I combine them linearly, and it gives me actually the position in my n dimension state here, and I can determine what was a class of my sound according to that. So here the weights are specific to a certain model that I train on. So I had actually to have seen some example of that kind of sound before, but after that, they remain constant for the same kind of sound I want to process. So that's actually the physics behind the physical reservoir computing implemented for audio into a microphone.
Are you creating a microphone characteristic specific for a circumstance that you want to classify, or are you saying that by having this nonlinear microphone, you automatically separate these components?
So the microphone itself, it's fixed. So the reservoir will always extract the feature the same way, but the model can be adapted for different classification. So you still need some adaptation of a model to be able to classify different things, but the reservoir itself stay the same. So what it's doing actually, if we compare that to other kind of technology for audio recognition, usually you will have a lot of components in the system to do the sound recognition. What we are doing differently here, we avoid the requirement of a DSP, essentially. You don't need any digital signal processing in order to do your classification, because everything is done directly in the microphone, which we call a physical reservoir computer microphone, PRC microphone. So here we have the input signal coming in the microphone, and then the output can be processed by a simple model, either on an MCU or either embedded directly into the ASIC of the microphone. So this is what actually we are designing at the moment. Okay. So any question on that so far?
No, well, somewhat get it. Yeah, keep going.
I know it's really deep physics, and it's why actually I decided to join the team at Echosonic. I have a background I'm a physicist, and I have a background in physics, and I was intrigued by this technology, how we can use a physical system as an analog computer, essentially, but in the dynamic. So that was crazy idea.
I do have a couple of questions. So the microphone itself, do you have multiple signal outputs?
Nope, it's all in one time series signal, but there's a way to know which state we were, at which moment we capture the signal. So we can relate that to the state of the microphone we were, and we can extract that way the different features.
Okay.
Make sense? Oh, and I forgot an important thing as well. Because a dynamic system has nonlinear effect, because it has deformation. Essentially, when you have a deformation of your physical system, it's where the nonlinear effects coming in, like distortion, when you have a deformation, the distortion coming in. So it has what we call also a memory effect. The fact that your system has still information from the time just before. And this is what creates I will just go back for a second. This is what creates the connection. Like when we were talking about recurrent neural network here, it's actually all connected neurons together. In the physical reservoir computer, you can recreate this connection by keeping a memory effect in your system. So the state of your microphone at a certain time still have some information of what happened just before. So what happened just before will have an impact on what will happen after. And this is what's connect together all the states of your microphone. And this is important in physical reservoir computing to have this memory effect. It adds actually even more complexity to your signal to be able to process even better. Here I can just tell you why actually this technology is interesting in a commercial point of view. Of course, we reduce the power consumption per inference because you don't have to transfer your signal to a DSP, the DSP to another chip, so there's less component in your system. Everything is done at the same place. In terms of capabilities, there's some technology that exists, like analog AI chip applied to audio, but the capabilities are really low at the moment, and the physical reservoir computing has not this constraint. In terms of cost, it's a microphone. It's a MEMS microphone, so it's in the same cost price as a microphone. In terms of training, this is also a huge parameter. Right now in audio processing and all kind of AI processing, it's a training cost. Here, the training is very limited because the model itself is super simple. Your features are so well distinctive that the model does not require a lot of what we call layers, I would say, or comparators in order to extract correctly or to be accurate in the classification. And most importantly, I just added here the conversion in MEMS spectrogram, which is the regular way when we do sound processing. We don't actually need this part here, which everybody else or every other techniques will require.
Okay.
So the microphone is actually a custom part. Do you take an existing microphone and modify it, or you have to develop the whole silicon, everything?
So at the moment, our objective is to use generic MEMS die and add our ASIC to it. So this is the kind of product we would like to have. We still have to characterize if we can get into the regime we need with just a generic mic. So we try actually different brands at the moment and see how it works with those different geometry. But the objective is really just to use something that already exists.
Okay.
A little bit out of our depth, I think, Dave, but I'll go on one step then. So if you take an existing microphone and you get an analog signal from that microphone, and then there's some other block which is introducing this nonlinearity.
I will come back here.
Yeah.
So we need to, you probably know how a MEMS microphone is built. So you have your MEMS die, your dynamic element, and you have your ASIC that control the mechanical element. So we need actually to be able to control the mechanical element. So the technology is embedded into this ASIC, which will communicate and will also have access to the output of this mechanical element. So this is needed. So this is the kind of final product, which is actually a MEMS microphone. But what we are focusing on is this ASIC here.
Mm.
And then what you get from this microphone is not a classic signal. You're getting something different from that?
That's a good point. So yes, the output of this this MEMS die, it's different from a regular one because we had modified the signal. But actually there's ways to recover the signal from the information we extract. We are able to recover the original audio, and even better, we can apply even more process during the recovery steps. You can actually try to remove some components that are unwanted, which could also act as a kind of a denoising step in your signal. So this is like the future, what we are planning in the future, but this is something that is not unbelievable, let's say.
The potential feature down the road.
So the concepts, is this something that is the underlying concept of it is something that's been around for a while, or is that quite a new revelation?
Physical reservoir computing is very popular in the research area. Implementation into commercial application and commercial product is less obvious because there was no easy way to do the implementation. And actually the IP that we had from this university at the North Carolina University allowed a better implementation, an implementation that is commercially viable, which wasn't the case with the other kind of physical reservoir development that has been done in the research side. So it's something that's well documented. You can find a good paper about physical reservoir, but how to integrate that into a device that is still affordable, efficient as well, because the whole idea here is to be efficient in terms of power. If you have a microphone that consumes more than the full system for sound recognition, it will not be adopted, even if the technology is cool. So you still need to have a low power consumption, and this is what the previous implementation were lacking. You needed some other component that was making your system not power efficient.
Okay.
I'd like to have more questions, but I'm a bit out of my depth, unfortunately.
Go ahead.
No, I don't know. I don't know what else to ask. I don't know how to attack this problem.
Okay.
It's too complicated.
Maybe I can tell you which kind of application that are interesting for that. We think there's a huge application in predictive maintenance for automotive, for industry, for what we call IIoT, something that requires to be always on. So always on, because this is the kind of technology that we tried really low power and can record all the time and just trigger a full system when there's a sound with a special meaning happen. So if you did an abnormal sound, for example, or a sound that has a meaning, like someone enter your room or enter a room and then you want to open something, this is the kind of always on triggers that this kind of device can perform efficiently. So this is a vertical that we're looking for at the moment. But still, we don't have a product on the market yet, but this is the roadmap.
Yeah, I mean, there's like security, like detecting glass breaking, or in automotive, you kind of touched on that earlier, like detecting alignment issues in automotive or industrial manufacturing applications. Like the traditional microphone guys put a lot of MEMS into manufacturing systems. People aren't really aware of that, but it's like detecting alignment, but they're obviously using a lot of back-end computing to detect is the roller in that mass production equipment aligned, or is it going off and creating inefficiencies, and the wear and tear on the machine, and also problems in production can be calculated quickly. With this.
And also for critical application, as I was mentioning before, when the latency is not acceptable, when you have leak of something, for example, you have to be fast to cut cut the line.
Yeah, like an oil leak, or like you say, mission critical stuff. Like I was reading about the train derailment in Palestine, Ohio last year, and the operator, the engineer of the train, didn't know there was a problem because there was a savings of a $1 sensor that could have been on the train wheel to detect a misalignment issue. So there's lots of applications. It's interesting.
And we don't think that much about it, but audio is a really efficient way to detect that there's something wrong. Like when you're driving your car, what are you doing? Like you listen to it and you see, oh, there's something wrong with the sound. Like you will not necessarily feel it or you will not see it, but you will rely on your auditory system in order to find that there's something problematic. So that's actually something we thought that it's an easy way to integrate our technology for this kind of application because it's already used to do the same thing.
Right. Cool. Okay. What else can we learn about this?
I told you everything.
You told us nothing. We want to know the secrets, the real.
Time I to understand this technology. So I guess if I succeed in 30 minutes to make you understand almost everything, I did my job well.
Yeah. Okay. So what should we talk about next in this presentation then?
Yeah, I can just continue briefly. So of course there's different market needs where this technology can be efficient, especially in, again, sound processing. But if we go more into the speech processing, we can also do what we call soft biometrics identification. Like you could, without any latency, having an identification of your own voice based on the different feature that's embedded into your voice, which is more complex actually than just audio recognition. You have your tone, you have your different speech intonation, pitch intonation and stuff like that. So it's actually a problem that the nonlinearity could actually handle better. And of course, in turn, we want to enter into the consumer electronics because MEMS microphone, of course, are the main microphone in the industry. And this will be a huge market for this kind of technology as well.
Yeah, for sure. Okay, so let's see here. That's what you need.
You can read it. Why it's actually important to find alternative to standard way in the semiconductor industry. There's actually a limit. At some point, we'll not be able to reduce those transducer smaller than maybe we are at 2 nanometers now, the technology actually. Anyway, It's super small and it's not as efficient as we are expecting because we reach the atomic limitation at the moment. So we have to find new ways to improve the processing powers. So physical reservoir, a new paradigm, the physical reservoir computing way to do computation could actually get over this limitation because we are not relying on reducing the transducer, but we are relying on using differently what we already have. So this is actually what Echosonic is aiming for, to revolutionize the way we are doing time signal processing by introducing this new way to do it.
Okay, very good. Okay, so I guess, Simon, you already confessed you have no more questions.
Thank you.
Okay, so if there's nothing else to add, I guess we'll put information on how people can get in touch with Echosonic if they're interested, I guess at this point, investing or partnerships, these kind of business variables that are good for early stage companies. And so I guess...
And maybe something, I will be at CES in January. I will in the Eureka Park, so maybe we can reach out over there.
Sure. Okay. Yeah. Well, I think, two of the three of us will be at CES. One will be on vacation in New Zealand, but okay. So yeah, Marie-Eve, thank you for joining us today, and we encourage everybody put a like and share, subscribe, all that good stuff, and we'll see you guys in the next episode. Thanks, everybody. Bye-bye.
Thanks.